Hi, my name is Aditya. I am the CEO of Automatski. Today we are going to be seeing protein ligand docking. Now, before I come to the demo, I'll explain a few things and then we are going to get into the exact demo. The name of the framework that we have developed is called Lotus Dock. It works on quantum annealing. Quantum annealers are a special type of quantum computers that can solve optimization problems. So docking is being posed as an optimization problem. It is running on Automatski's annealers, which support up to 500 million qubits or Boolean variables. Automatski's quantum computers also support up hundreds of logical qubits and millions of gates. So we are going to get into this, but before that, you have to understand that molecular docking takes anywhere between a few minutes to several hours for a single ligand protein complex. And it depends on the complexity of molecules and the search space, with virtual screening of large libraries taking days or weeks. Simple docking runs on online platforms can finish in 1 to 2 minutes, but they require hundreds of gigabytes of RAM, GPU based servers, and very advanced processors. So it typically demo takes a workstation, but we have a normal laptop before us, and I'm going to do everything in real time. I'm not going to pause the video. A lot of people say that Automatski does not have any quantum computers and it uses heuristics and classical shortcuts. It uses HPC clusters and supercomputers in its demos of more than 50 logical qubits. But the truth is that supercomputers cost a minimum of $100 million, upwards of $1 billion, and Automatsky does not have that kind of money. But to silence these kind of critics or people, we have released the entire source code of the demo that we're going to show you today. The entire protein ligand docking framework, which is Lotus, and you can access this repository. It is public, and now I'll explain what is here. There is a requirements.txt. You can install the dependencies. There is a way to make Docker containers. Run server will run the server, and so that you can get the UI, this UI on which you can uh, do your docking. Uh, there is examples folder with lots of proteins and ligands inside it. The proteins are in the form of protein database files, PDB, and ligands are in the form of SDF files or ligands. Now, why is this important? Why why is this going to probably become the single biggest commercial application of quantum annealers? And why this will change pharmacy? Because the ability to do fast and accurate docking directly impacts drug discovery timelines, compressing them by an order of magnitude. It impacts cancer therapeutics, rare disease research, pandemic response, precision medicine, protein engineering, and molecular design. A single breakthrough in docking accuracy can save years of pharmaceutical R&D effort and potentially billions of dollars in failed wet lab experimentation. That is why what I'm going to show you today may become one of the single biggest commercial applications of quantum annealers. So there are two things primarily uh, in pharmaceutical engineering. The first thing is to understand the properties and structure of proteins where you need to do protein folding. And the second thing is to do protein ligand docking. Now, ligand is a biomedical word or a molecular biology word, but what it means is that medicines like aspirin, etc., dock to proteins and then they inhibit or accelerate some activity of the protein which causes the disease to end. That is why protein ligand docking is probably one of the biggest problems that need to be solved. Here I have a ligand smile string examples text. So in that you can see this is the aspirin molecule here. You can use this in your examples while running chlorobenzene, ethanol, benzene, and some drug-like complexes. This is a drug-like complex, so you can use this, and you can install the requirements in a Python environment. You can run the server on Windows, Linux, Mac, etc. You can also download Automatski's Quantum SDKs, which are free for both annealing and gate-based quantum computing. And the Automatski's Quantum Playground is also free, which works on Windows, Ubuntu Debian, and Mac M1 to M5. You can download those and try them out. There is a demo video you can see, which will be this video. You can see here. Now let's get into Lotus Dock. So Lotus Dock is organized into multiple tabs. The first tab is to import the protein. You can give the protein ID and import it from RCSB database. You can import a universal protein ID based protein from AlphaFold, or you can upload a file, a protein database file, or MMCIF or pdb.gz. To import the ligand, the first thing you can do is you can give a smile string. Smile string is a string of molecular representation of a chemical compound, a bio compound. And there is a default value here you can use. This is aspirin, or you can use one from the text file or from any source that you want. The second way is to upload a SDF file from the hard disk from the examples folder, or a mol2 pdbqt or a batch CSV. Pocket detection is used to detect pockets on the protein. What is a pocket? A pocket is basically a hole or a cavity in the protein which has a high probability of the ligand docking into. You can do pocket detection using multiple algorithms, grid-based, energy-based. Grid-based is the fastest, energy-based is the slowest, or you could use all methods, etc. This is the actual docking tab where you allocate a certain number of bits for translation, for rotation and torsion. What is translation, rotation, and torsion? Basically, the ligand can move around the x and y axis, that is translation. It can rotate around the x and y axis, that is rotation. And it can twist and turn, which is called torsion. 8 bits means 2 to the power 8. The space will be quantized into 2 to the power 8 areas, and it will be analyzed. Annealer threads and other, these are some options that are used for development but not required. This is the screen where you can visualize the dot complex, the binding pocket, multiple poses, etc. This is the benchmarking screen tab where you can benchmark the implementation on the Aztecs diverse 30 case database, and you can select the number of cases to run, and you can run the benchmark. Though I have to warn you that the precision of the framework has been limited to 1 angstrom, and the benchmark will not result in top 5 results of the world. This has been done on purpose because this is actually our IP and we want to hold on to the most accurate functionality. This is the settings screen. Everything will run on the Automatski annealer, and you can set the Automatski annealer configuration. Here you can see local host and 8000, but we have developed our own post-quantum cryptography based VPN software, which creates a tunnel between my laptop and the local area network in the office to the site where we have our annealers and gate-based quantum computers. And that requires post-quantum cryptography, secret keys, and public keys. So that is a hard-coded thing in the backend. We'll remove it when we have removed it when we publish it to the GitHub repo. So you'll actually be putting the IP address of the annealer, and then you can run this. So let's get started. I'm going to upload a protein file. This is a protein database file that is kept on the hard disk from the examples folder. I load it. It takes a second. It loads. I'm going to load the ligand. I'm not going to use aspirin or any other smile string. I'm going to load an SDF file from the examples folder. And let's do this. Now I'm going to do grid-based pocket detection. That's probably the fastest. It will take a couple of seconds and it has detected the top 10 grids with different grid scores, and you can select whichever grid, but this is not required because docking will do its own grid detection. So I'm using 8 bits for translation, rotation, and torsion. You can increase it to 20. 20 will mean that 2 to the power 20, which is around a million partitions in X and Y axis, translation, rotation, and torsion. That is probably way more than production grade requirements. So let's run this. And I'm not going to stop the video. I'm going to let this run. So like I was saying, this is running on Automatski's annealers. These are the latest generation of our annealers, which support up to 500 million qubits or Boolean variables. And even for running problems with 100 million qubits, they take only seconds. Uh, but the denser the problem, the more time it will take in both formulating the problem and sending it over the network, solving it and receiving the result. So, but the annealer itself will take seconds to solve such problems. So what is happening here behind the scenes is that there are a lot of calculations going on that are used to formulate the problem and the QUBO model. And then the QUBO model is sent to the annealer for execution, and the results are gotten back and are post processed. And then you figure out the score and the poses, etc. Now, Lotus Dock is an industrial strength production grade framework. And why we say this is a world record? Because this is the most advanced quantum annealing based protein ligand docking framework in the entire world today. And uh, you can look at the source code. There are no classical shortcuts. It's everything is done on quantum computers, and the critics can. Okay, the docking has been completed, and 20 poses with the best pose minus 60-degree kilocal per mole. Runtime 113 seconds. Like I said, I did not stop the video. Here are all the breakup of the energy calculations. These are extracted from the QUBO model. I'm good. Oh, it makes sense to visualize it. So this is the protein, and you see this thing here. This is the ligand. So the proximity of the ligand to the protein is around 1 angstrom, and we need to do better for large scale applications. But this is what we have released in open source. You can verify the open source and you can get in touch with us. Let us know how we can help you. Anybody from the pharma industry, cancer therapeutics, or molecular design, please get in touch with us and let us know how we can help you. That's all we had for you today. Thank you very much.